Okay, welcome everyone to this edition of the BRAG, Brazilian Algebraic Geometry Seminar. And it's a pleasure for me to introduce our speaker today, who is Valeriano Lanza from UFF, Universidade Federal Fluminense. And he will tell us about moduli spaces of flags of sheaves, a quiver description. Please, Valeriano.
Okay. Thank you, Carolina. And first of all, of course, I want to thank all the organizers for inviting me. It is a pleasure to give this talk today. And so, as the title suggests, I will speak about moduli spaces of flags of sheaves. And in particular, I want to present the content of this very recent paper together of mine, together with Rodrigo von Flach and Marcos Jardim, which is a natural prosecution, actually, of a previous work of the first two authors, Rodrigo and Marcos, of 2017, based on the PhD thesis of Rodrigo. So actually, to understand which is the more recent contribution, I will also give a review of the main results of the first paper. So, as the title suggests, we are talking about flags of sheaves with a very particular point of view. We want to basically describe these moduli spaces through as moduli spaces of representations, stable representations of an appropriate quiver. So let's first focus on the, let's say, more geometric side of the picture. So, of course, if we are talking about flags of sheaves, framed flags of sheaves, let me give the precise definition. So, in general, I will work on the complex numbers. Okay, so sorry that I didn't mention it immediately. So, a framed flag of sheaves, framed flag of sheaves for us on P2 will be a triple, let's say F phi, where, well, F is a torsion-free sheaf. On P2. Phi is the so-called framing. It's a fixed isomorphism between the restriction of our sheaf to the line at infinity of P2 and the trivial bundle of the appropriate rank. This is a fixed isomorphism called the framing. The third guy that appears here, E, is instead, of course, if we're talking about flags, it will be a subsheaf of F, such that we're requiring that the quotient F over E is supported away from the line at infinity. So this in particular implies that E and F so have the same rank, and both actually have vanishing first Chern class because of the presence of the framing that gives a restraint about the intersection, of course, with the divisor given by the line at infinity. Okay, so these are the objects we want to study, and from that, of course, we want to build a moduli space of such objects. To do so, we need to fix invariants, and so we will have the rank of the sheaves involved, which we will call R, rank of F, which is the same as the rank of E. Then, as I already said, the framing, the triviality along L-infinity implies that both first chain classes of E and F vanishes because they are framed. Framing. Okay, so another invariant will be the second chain class of F that we shall denote by N. And finally, we have actually a couple of choices. In the paper of 2017, Rodrigo and Marcos chose to use L as invariant, which is simply the H0 of F over E. This implies, of course, that I want to write it down explicitly because then on the quiver side of the picture it will be relevant. Then the second chain class of E is actually N plus L. Okay, so I won't enter the details of how one can build this moduli space, but we have this fine moduli space, which is F, which we shall denote by F of R N L. Okay, so this is just a very short introduction about the main geometrical objects we are dealing with. But we shall use quivers, representations of quivers to describe this moduli space. So let's quickly recall what is a quiver and what is a representation. So a quiver is simply a finite oriented graph. So in other words, we have just to give a bunch of vertices and a bunch of arrows, okay? And a representation of a quiver is given by a choice, a representation of quiver Q is given by choosing one vector space associated to every vertex and one linear map associated to every arrow. Okay, this is completely equivalent to say that we are interested in representing the so-called path algebra of the quiver. So this is the same as consider a representation of the path, the so-called path algebra, CQ of the quiver. Let me also just mention that it is possible, and we will do so, to consider quiver with relations. In other words, we are modeling out the path algebra by an ideal, okay? And representing a quiver with a relation means that we are considering linear maps satisfying some closed equation, some condition, okay, that can be expressed through to an equation, okay. And this is actually what one usually do, for instance, when such a quiver description arises, for instance, through a symplectic reduction, as we shall see in a moment. Okay, so of course, when we want to describe a specific modular space as a modular space of quiver representations, we need to fix a specific quiver. In this particular setting, the quiver we're dealing with is the so-called enhanced ADHM quiver, which is a quiver with 3 vertices that I'm denoting by 1, I'm labeling by 1 prime, and infinity. And this set of arrows, and now by abuse of notation, I'm already calling the arrows with the name I will use for the linear maps when considering a representation of this quiver. Why it is called enhanced ADHM quiver, and why it should be kind of natural to associate this quiver with the problem of describing flags of frame sheaves. The answer is very simple, because if we just focus on the right side here, this part that I circled in yellow, this is a very well-known quiver called precisely the IDHM quiver. This acronym ADHM stands for Attila, Drinfeld, Hitchin, and Manin, the first authors in literature that used not actually a quiver description of a modular space, in particular of instantons on S4, if I remember properly, but at least they used linear data called precisely the ADHM data to provide such a description. In particular, this quiver appears in a pivotal work by Nakajima, 1999, where precisely he described framed sheaves on P2. So it is kind of natural that to describe instead flags of framed sheaves, we have to take the original quiver, the original ADHM quiver, and add something, add some data. In this case, these 3 additional arrows and vertex 1. Okay, so of course, the main result, one of the main results of the paper of 2017 will be, was actually, okay, in the past, was to provide an isomorphism, so between this modular space F, R, and L, and a suitable modular space of stable representations of this enhanced ADHM quiver. So what we want to do is to build now a modular space of quiver representations. We want to build a modular space of representations of the enhanced ADHM quiver. To do so, we use a recipe provided by King, King's recipe. Uh, 1994, which is basically a GIT construction adapted in the situation of representations of finite dimensional algebras in general, as a main example of applications for representations of a quiver. So GIT construction. So basically, we want to construct a moduli space and RC C prime, first thing first, we need to fix invariants. In the case of a quiver representation, the invariants, of course, are the dimensions of the vector spaces attached to the vertices of our quiver. So in this case, we shall have 3 natural numbers. So this is the dimension vector, let's say. So R will be the dimension of the vector space W attached with the vertex infinity. C will be the dimension of the vector space V attached to the vertex 1, and C prime the dimension of V prime attached to the vertex 1 prime. So once we have fixed the invariants, we should introduce a suitable notion of stability. Before doing so, as anticipated before, we actually add also relations to this quiver. So we add relations, which are these equations. So commutator of IAB plus IJ equals 0, then commutator of A prime and B prime equals 0, then BF minus FB prime equals AB AF minus FA prime equals JF equals 0. Why these should be natural relations to consider? Yes, one small observation. I started immediately going straight to the point without providing some motivations of why these objects, these moduli spaces should be of some interest, but I will comment this later on, so it is a bit of a strange order in my presentation, but you will understand, I hope, later why I chose to do so.
Valeriano,
yes.
These relations are between the maps of the representation you showed? A, B.
Yes, so in principle, these are relations. It's basically an ideal of the path algebra of this quiver, okay? In practice, what happens is that we are just considering a representation whose linear maps satisfy these relations here.
Correct.
Precisely. So this first relation is the so-called Adhm equation. So this is just taken from Nakajima's work. This is the Adhm equation. And as for the others, I will comment what they want to represent in a while. This first is kind of natural, because if we have this sub-quiver, which is the Adhm quiver, and we want to really extend the data, in particular, this part of the datum has to satisfy the same relation that appears in Nakajima's work. So this is kind of natural. Perfect. And then, as I was saying before, we have to introduce a notion of stability that it will be precisely at the end of the story a GIT stability, but for us, we will just trust King's work and so apply the prescription given by his paper. So a stability, a notion of stability depends on the choice of a parameter theta. A parameter theta, which is of the form of theta infinity, theta prime. So actually it's a triple of parameters, of real parameters. In general, the prescription is to take a parameter in R to the I, where I is the space of vertices of the quiver. In this case, we have 3 vertices, and so we have an element of R3, such that this condition is verified. R theta infinity plus C theta plus C prime theta prime equals 0. This is just a normalization. It's nothing with a deep meaning. And actually, there is a subsequent work by Rudakov, stability for abelian categories, where it is really showed that it is very easy to see that it's completely not substantial. Okay, but in order to simplify the analysis, it's way better to use this condition, to put this condition. So this is like a sort of normalization. Okay. So given a specific parameter theta, what is a theta semi-stable or a theta-stable representation of the quiver? I already, oh, sorry, it's a bit annoying. Okay, I already wrote here all the whole definition. Basically, it's a slope stability adapted in this context of quivers. So we are considering all possible sub-representations of the given representation. What is a sub-representation? And it's just a collection of subspaces of the 3 vector spaces that we fixed, which are invariant. Invariant subspaces, it means that they are respected by all the linear maps of the representation we are considering. And we say that a sub-representation is of numerical type R tilde, C tilde, C line, C prime tilde, if the dimension of the 3 subspaces are precisely these 3 natural numbers. Then a representation is said to be theta semi-stable if these conditions are satisfied. Here we are just restricting ourselves to non-trivial representations, and here to proper representations. So let's skip a bit here the details, the technicalities of why we are just considering 0 or R here as possible dimensions for the subspace of W, or why here it's just non-trivial but proper, it's just here. Let's skip a bit these technicalities. The meaning here is precisely a slope substability. Why? Because the normalization condition that we put before can be rephrased by saying that we are taking the stability parameter in such a way that every RCC prime dimensional representation has slope 0. So this inequality will be the slope of the sub-representation lesser or equal than the slope of the whole representation, which is automatically 0 because of this choice that we made, which is always possible to do. As always, when there is the strict inequality, we are talking about stability. When the equal is also allowed, we are talking about theta semi-stability. Okay. Perfect. So we have almost all the ingredients. What we have to do finally, of course, to perform a GLT and build the modular space is to let a linear, an algebraic group to act. So we also have, of course, the action of the group. What is the action for a representation of a quiver? It's the natural one. We put here, here, and here vector spaces, but we want to ignore change of basis, of course, that don't change the essence of the data that we are considering. So we are modding out, in principle, by the action of GLV times GLV prime times GLW, in principle, if this would be a simple, not in a technical meaning, representation of a quiver, but actually, as on the geometric side we had framed flags of sheaves, also here we shall consider only framed representations. So the fact that I chose to name this vertex infinity, it wasn't arbitrary, but random, but it's because this is indeed a framing vertex. There is a theory of framings for quivers, very well explained, for instance, in the lectures by Ginsburg, framing vertex. And in other words, as in the geometrical side, we fixed an isomorphism to this trivial sheaf along a divisor, here we shall fix a basis for the vector space attached to this framing vertex. In other words, we are not allowed to change basis here. So the true action of the group is just given by GLV times GLV prime. GLW does not act through change of basis. Okay, so we won't enter again the details, but we have all of these by choosing a specific parameter theta, we can build, let's say, a modular space n depending on the parameter theta, R C prime. So modular space of stable framed representations of Q ADHM enhanced with the fixed dimension vector, of course. Okay, so what is the theorem, the result of Rodrigo, by Rodrigo and Marcos, 2017, is that there exists an isomorphism of schemes between n theta r n plus l and f r and l if we choose the parameter theta in here. So once we normalize, basically theta infinity disappear from the picture, of course. So we can represent the space of stability parameters as an R2 between theta and theta prime. And the stability parameter has to be chosen inside an open cone here, this in particular, this open cone. Okay, where this line is the line theta prime equals minus theta over c prime. Okay, so just here at the level of the statement of this theorem, there is the first contribution of mine, I mean, of this new paper that was recently published, where I also participated. Because in fact, this open cone wasn't sharp in the sense that it wasn't really a chamber in the space here of stability parameters. It's a space of stability parameters. So we enlarged this cone, arriving to the true chamber, if we can say so, which is actually independent by the invariant C prime. It's delimited by always the negative semi-axis of theta, and the line theta prime equals minus theta. So this is true chamber. Plus. What does it mean? It means that in here all parameters are generic, which means that stability and semi-stability coincide actually. And we explicitly found on the open rays here, which are then walls of the chamber, strictly semi-stable representations. So it's just an algebraic side issue here. Okay, this is already a small an improvement, okay, of the first result, an enlargement more than an improvement. Okay, perfect. Now I won't give the proof of this result, but I want just to make a few vocal comments just to explain the idea through the picture here. Because we said that this ADHM, this part of the enhanced ADHM quiver is precisely the original ADHM quiver. So it is natural to assume that this part of the data should describe one of the two sheaves involved here. It might be E or it might be F. Actually, looking at Nakajima's work, the two dimensions that we should put here are precisely the rank and the second Chern class. So as the dimension here in the statement of the theorem is n plus L, you should be convinced that this data here will identify precisely E, the subsheaf with higher second Chern class. Of course, to do so, we have to be sure that the choice of our parameter, theta, inside here the chamber, ensures that these data A, B, I, and J are stable in the sense of Nakajima, which is in fact true. Then where we can recover the other sheaf F. If you want, we can interpret here this picture in a slightly different way by adding here as kind of a ghost vertex and actually 3 ghost arrows. Why? And in other words, it's a bit like as if we consider this big quiver and then put here dimension 0. Okay, dimension 0 here. Why we would like to do so? Because then this might basically represent the quotient F over E. In fact, the H0 F over E is precisely L, which is the dimension of the vertex that we put in this vertex here, and the rank would be precisely 0. But so this other part of the data do not identify the sheaf F, but the quotient. In fact, the sheaf F is recovered by considering a quotient here of these 2 representations, because the choice of the stability parameter in here also ensures that the map F is injective, so that we can interpret the whole picture as a monomorphism in the category of representations of the original ADHM quiver. Okay, and so then by modding out, we would get other data to the quotient. Of course, one has to prove that they are indeed stable and that actually they identify the other sheaf F. So if you want, at the end of the day, we have sort of a contravariant functor, because E is the subsheaf, but at the level of the quiver representations, F is represented by a quotient of the data representing E. So a sort of contravariant functor between the category of sheaves and the category of representations of this quiver. If you want a fancy way to describe a bit what's happening or why this actually works. Okay, so finally, I want to give some motivations. So why these quivers are interesting. And I want to mention at least these 2 works. The first one by Bruzzo, Zhuang, Diaconescu, proprio Marcus, Pan, and Zhang of 2011. They are, and the second one is a very recent work by Bonelli, Fasola, and Tanzini, and both are have a very physical flavor. So as much as I'm not able to actually explain what is the physical meaning, let's just say that this quiver these quivers arise describing this sort of brains or surface defects, which is some quantum mechanical string theory nonsense that I don't really know. I want just to mention that in both these works, they are not actually dealing with precisely the enhanced ADHM quiver. In the first one, they add one more relation, if you want, which is A prime equals B prime, or in another way, you can say that they are gluing the 2 arrows. While in the work of Bonelli, Fasola, Tanzini, actually this enhanced ADHM quiver is the basic building block of the quivers they are considering, which are way longer and much more complicated, because basically they are studying longer flags of sheaves. Okay. It is worth mentioning that for the computations, the physical computations that both these works want to do, some result about smoothness, if you want, of our moduli spaces are required. So the goal would be to try to prove at least some regularity or some result about precisely the problem of the smoothness of the modular spaces we introduced. Unfortunately, there was a result, a stronger result in the paper of 2017 that for a specific choice of C prime, we shall discuss later a bit more in details. These modular spaces were actually smooth, but unfortunately there was a flaw in the proof, and so it is not valid anymore. But what we could prove, sorry, I'm spoiling a bit, it was that at least theorem, all these modular spaces have a perfect obstruction theory. So, Flach. Okay, so N R C prime has a perfect obstruction theory. Emilio Franco in the last week's seminar made a beautiful review about these topics. But what we mean is that we can write down a deformation complex for every representation, okay, which has this shape because we have to linearize before the action of the group. Then we shall linearize the relations, but the relations are not independent among them, so it arises another differential here, and these are the huge maps involved that I wrote before, because if not, it would last forever. Okay, so basically we studied the deformations here. And to say that the modular space has a perfect obstruction theory is equivalent to say, which means that for every representation, we have the vanishing of both H0 and H3 of the deformation complex. So in other words, we can really identify the H1 as the deformation tangent space to the moduli, and the H2 with the obstruction space. In particular, first, I want to mention that this result is already sufficient for the physicists to perform their computations. So even with, of course, smoothness then is a natural question, that a natural topic that we want to inspect as mathematicians, but at least already this fact is enough for their purposes. And of course, this allows us as a nice feature to compute the expected dimension. Expected dimension, which is R times 2C minus C prime when C prime is greater than 1, and R 2C minus 1 plus 1 when C prime equals 1. Why there is this difference? It's because when C prime equals 1, here we have a lot of extra commutations, because all the primed guys are just now complex numbers, basically. So at the end of the day, this summand here is not does not play an active role when computing the expected dimension. Okay. Very well. So in these last minutes, I would like to present a bit more in details, which are the open problems that are left to investigate. And as I was saying before, first natural question is about smoothness. More specifically, a good question is the following. If when C prime equals 1, the moduli spaces we are considering are smooth or not. Why should it be so? Why this C prime equals 1 has a special role in the picture? Because when we focus on the rank 1 case, actually, framed flags of sheaves on P2 can be interpreted as nested Hilbert schemes of C2. Okay, and these objects were already studied in literature independently from this quiver description. And in particular, it is well known since 1998, and this paper by Chea, I don't know the precise pronunciation, sorry, that N1CC prime is smooth precisely when C prime equals 1. So nested Hilbert schemes are just two zero-dimensional subschemes encapsulated one into the other, and when the difference of the number of points is just 1, these nested Hilbert schemes are smooth, and when instead the difference is greater, they are not. Of course, once we have here developed a deformation theory, one could try to put the hand with the matrices and do computations in linear algebra. But unfortunately, the complexity or the computational complexity increased very, very quickly when the invariants also increase. But for instance, at least in this with these small numbers 3, 2, so C equals 3 and C prime equals 2 for any rank, we can really see that the dimensions of H1 and H2 jump, and so they are indeed singular. The case C prime equals 1, which was precisely the one that was stated in the paper of 2017 to be smooth, is still open. But at least with these algebraic tools, it seems a bit too complex to be faced. Okay, so we hope maybe we are not watching at the right part of the picture, but so far is still open. Of course, we would hope that our their ADHM data will be helpful in order to solve this problem. And a final natural other problem involves so yes, one result in this direction, I mean, not really strong in this direction, but which adds something more, is this other proposition that we might prove that in this case, at least, we can find a family of unobstructed points. So, okay, in particular, this means that the moduli space is at least generically unobstructed. And explicitly here, we would have a family of unobstructed points. It's very simple set of data, and basically here, by choosing diagonal matrices with distinct eigenvalues, what happens is that stability arises almost for free, because when you apply powers of these linear maps to get invariants, you would get basically a van der Monde determinant, so that at the end of the day you would invade the whole space. So there are not many sub-representations where one should check stability. Okay, so one final open problem is about connectedness and irreducibility of these moduli spaces. I want to mention that even if so far we do not have results, the idea would be to use our ADHM description, quiver description, together with the fact that there is a natural projection from our moduli spaces to MRC minus C prime, because here we had N plus L, here we had L, and the second Chern class of F was N, so the difference. And this is basically a forgetful map. We are forgetting the fact that we have also some sheaf. We're just considering the data F phi as a usual framed sheaf on P2. And it is known that Nakajima's moduli spaces are smooth and irreducible and connected. So one idea would be to try to use our explicit description to describe the fibers of this map, and maybe trying at least to get a connectedness for some maybe specific choice of invariants gluing together to the base of this vibration, the whole moduli space. So this is for the future. And another possible developments would be trying to perform a wall crossing study of this picture here. We detect which is precisely the chamber, but it would be interesting to cross the walls and try to do variation of stability here. Okay, so I think that more or less I said everything, and I have an alarm, so perfect. And I can stop here. Thank you.
Thank you, Valeriano. Are there questions or comments for Valeriano?
I have one.
Yes.
I think in the slide where you define the theta stability or semi-stability, I couldn't understand properly your definition.
This one?
Yeah. If you remember, you called this product theta the slope of the subrepresentation.
See, it is a slope-like stability. Yes.
All right. In the same line, in the right side, you wrote that for all mutual subrepresentation of numerical type 0, C, C prime, how
Non-trivial here.
Yeah. So I cannot see how this parameter 0, C, and C prime depends on the subrepresentation.
No, I mean, for every subrepresentation, we should consider the dimension vector that I called 0, C, tilde, C, tilde prime, okay? And then, so this is the slope of the subrepresentation, because it's the parameter theta, scalar product, the dimension vector of the subrepresentation. Here there is this point that I stressed that it seems a bit strange that we are not allowing other than 0 or R in the framing vertex. But I would prefer not to enter these details because it involves a Crowley-Bovey, a trick introduced by Crowley-Bovey, and actually the framing vertex should be considered as a one-dimensional vertex, multiplying then the number of arrows and so forth. So basically,
I think his doubt is about the quantifier. You don't need for any, just for some.
Yeah, exactly. I mean, the definition seems to depend on the numerical parameter, but when you write on the right that for all subrepresentation, I thought that in some way the maps of the representation would play some role
No, so a representation is theta stable, for instance, if for every non-trivial sub-representation with dimension vector
right.
0, c tilde prime, we have this inequality.
All right. So what
Sorry,
you
maybe
call
it's the order in which I wrote this, but
so what you wrote numerical type is
usually one would say for every non-trivial sub-representation with dimension vector c tilde prime, such that the right-sided subspace is contained in the kernel of J. We want this, and then for other with the right including the image of I. I don't know if it's clear. I don't like too much actually this.
If I understood his doubt, he would be happier if you phrased your condition if there exists a sub-representation of numerical type 0, c tilde prime, then theta times blah is smaller than 0.
Oh, I couldn't understand right now.
Okay.
So I think that's
sorry if I wrote it in a confused way. I apologize.
More questions?
Thank you for your questions again.
All right.
More questions or comments? I have a naive question. So you discussed that moduli space in that range, in that chamber, but do you know what do you know about the geometry of this moduli space? Do you know some birational invariants? Do you know the birational class? I mean, what is the geometry of this moduli space?
You mean well? Sorry, one moment. So the answer is probably that I don't know so much, but you mean of the but it's the same. The moduli space, the geometrical one or the algebraic one, right? So I don't really know so much. I mean, all the problems that I wrote before are still open. So,
but do you expect what is there any expectation of what should happen in the wall crossing?
No, not yet. No. It's like no, because there is no many examples in literature actually with quivers and wall crossing. I can mention one by Nakajima and Yoshioka, where they consider frame sheaves on the blow up of P2, which would be the first Hildebrand surface. And there they could actually do a complete wall crossing and actually get basically moduli spaces of Perver's sheaves, if I remember correctly. And at the end, they actually are able to connect through birational, like, with the birational transformations through all the walls, this moduli space with the moduli space on the blow down that is on P2. But in this case, so far, we have no idea actually. I also worked in my PhD thesis with framed sheaves in general over Hildebrand surfaces, not flags, but just framed sheaves, by getting a quiver description for the rank 1 case, so for Hilbert schemes. And even there, we are actually, it's a work in progress to understand the whole picture of variation of stability. And our current approach is actually to try to develop completely the investigation on the algebraic side. So like, let's really see the representations of the past algebra side, and by changing stability, how the moduli space of stable representations would change, and then try to figure out if there is then a deeper meaning of this other possible modular space that we would get. But we are really still at the very beginning of this investigation, so I'm not able to foresee any possible result, apart from this very interesting paper by Nakajima and Yoshioka, but doing an induction with just one case, it's not very wise, so I'm not really able to answer this question. Sorry.
Thank you very much. So are there more questions or comments? If not, let's thank Valeriano again.
Thank you.